All right, so this is lesson 7-7, simulate compound events. If you're wondering about the page number, it looks like it's page 411 in your workbooks. But this is going to be looking at different compound events to be able to approximate the probability. So with this solve and discuss it, Jillian lands on a beanbag board or beanbag on a board in about half of her attempts in its cornhole. How can she predict the number of times she will get the beanbag in the hole in their next 5 attempts using a coin toss? So you have to think about this just for a minute. With this, she lands on the board about half of her attempts. So that just means if she throws it 10 total times, she made it 5 of those times. If she threw the bag 12 times, then she made it 6 of those times. We can go up no matter how many times she threw the bag. Our outcome should be 1/2 of the time. So how can we relate this to a coin toss? Well, think about what a coin toss is. It is either heads or tails. So in our coin toss, you will either get heads or you will get tails. Both of these are or have a probability of 1/2. So how can we relate this cornhole game to a heads or tail flip or a coin toss? We can just say that if this coin toss lands on tails, we can say that the bag will land on the board, and then vice versa. Say if it lands on heads, and we can say that the beanbag did not land on the board. So with that, we're just going to write that out. So we can represent the coin toss has the same probability as her beanbag throws. So with that, because of the fact that the coin toss has the same probability as her beanbag throw, we can also state that if you flip the coin 5 times, because that's what we're looking for. How can we protect the number of games if we have these 5 attempts? Number of times she will get the beanbag, attempt 5 times using a coin. So if you flip this coin 5 times, it will represent her beanbag throws. So that's what we're doing. We're going to be looking at different scenarios and comparing them to compound events. Now, even though cornhole is a game, her first event would be her first bag. The second event would be that second bag. All the way down to her 5th event being her 5th bag. So that's where these compound events come from. Keep in mind your compound event is just more than one event happening. So a compound event is going to be more than one event happening. How might this be useful? So it might be useful to model scenario when it's easier to use a coin rather than actually her throwing this beanbag. So just for convenience, I mean, when might it be useful to model a scenario with a coin or the tool? When it is more convenient than conducting the experiment. And I'll even put events there since we talk a lot about events in this course, especially whenever we're looking at probability. Sometimes it is a lot easier to model something rather than actually conducting the experiment or the event. And so you're going to have to be able to judge when to conduct the event as well as when to then model it a different way. So with that in mind, we're able to look at example number 1. So example number 1 is simulating a probability situation using a spinner. Now, we use a spinner all the time in my classes, especially whenever we're deciding who is going to answer a particular question that's up on the board. They're using this spinner. Nikki is planning a hike for the end of the week. She really does not want to hike if it is raining the whole time, but is okay if it's cloudy. Based on the weather forecast, should she postpone the hike? Well, keep in mind this weather forecast, very similar to our weather forecast, this is a 40% chance of rain. So step 1 is developing that probability. So the sample space is either rain or no rain. It's either going to rain or it's not. Listing the 2 possible events, the probability of it raining is 40%. And we get that from that table, that saying that every single day it's 40% chance of rain. So with that, the probability of it not raining would be 60%. Now, you can set it up by 1. We learned that at the very beginning, that 1 is 100% chance. So that is good to know, especially since they kept it as a fraction. But just keep in mind, to subtract fractions, you need to have that common denominator. So this 1 would represent your 10 out of 10. That is your 1, and that's how they got that 6 out of 10 probability for that no rain. And then it even gave you that little tidbit of information as well. Now, say if you do not like fractions, you could always look at it as percentages. 100% minus 40% will give you that 60%, but it really just depends on how you work best with learning. If you don't like fractions, do it as percentages. If you don't like fractions or percentages, do it as decimals. You could also put this as 1 minus 0.4, and that would give you your 0.6 as well. So it's all about what works best for you. Looking at this, we have design a simulation using a spinner. This is a vocab word, so if you could highlight it, that would be fantastic. A simulation is going to be a model of the real world situation that can be used to find different probabilities. So this probability has outcomes and probabilities that would match the real world. Notice here that all they did to this fraction is reduce it. We can reduce 4 over 10 into 2 over 5. Notice how that correlates. The probability of it raining can also be written as 2 over 5. So therefore, we have 2 chances out of all 5 for this spinner. So that's something good to note too. And then from here, she said, well, let's run the simulation. Let's spin the spinner 3 times and record for each day. And she recorded it a couple of times because the more trials you have, the more accurate the data. And I am going to write that little note off to the side. More trials equals better data, which we like. We like better data a lot. So with that, she's conducting these trials, and For trial 1, the first day, it's going to rain. But yet this next 2 days, it's not going to rain. So we got 1 day of rain and then 2 not days. She does this a couple more times. We got no rain for trial 2, no rain, rain, no rain. Trial 3, rain, rain, no rain. Trial 4, it has all 4 days of not raining, which is great. And then trial 5, it has 1 day of raining and then 2 no rains. Based on this stipulation, Nikki should expect it to rain just about 1 out of the 3 days. And I mean, because of that, if it's only going to rain 1 day, then she's not going to postpone her hike. She's still going to go hiking. So hopefully her prediction is correct. Because keep in mind, with all these probabilities, we are focused primarily on educated guesses. Because at the end of the day, we don't know what Mother Nature is going to do. We've seen completely sunny days and then it have a torrential downpour just a couple hours later. I mean, we really do not know what actually is going to happen, but we can make a good educated guess and base our decision from there. Which does bring us for the try it. Now, I am going to help you out with this one because with probability, it is a little bit tricky. Educated guesses are not straight up facts. I'm very much factual. I am very much, it's either black or white. Give me a problem and let me solve it. So whenever it comes to probability, it's very good to get as much practice as humanly possible. So here it says there's a 50% chance that a volleyball team will win any one of its 4 remaining games this year. A spinner with 2 equal sections numbered 1 and 2. So keep in mind what they did here. They numbered 1 as a win and 2 as that loss. Is used to simulate the probability that the team will win exactly 2 of its last 4 games. The results of the simulation are shown below. So it's lining this up here as first to last game. All these are different simulations. So the first time they win 2 and lose 2, that is what we're looking for. The next game, it looks like they win 3 and lose 1, which is great, but not what we're looking for. The third one, 2 losses, 2 wins. Fourth one, 2 losses, 2 wins. Fifth one, it's 3 losses and 1 win, which is not great. Sixth one, 3 losses, 1 win. We have another 2 win, 2 loss. This one's great. We love whenever we all win, but it's not what we're looking for. The next one, 1 loss, 3 loses. And then after that, we have 3 wins and 1 loss. Keep in mind, we are looking for the answer of winning exactly 2 of the last 4 games. So the only ones we care about are the ones that have 2 wins and 2 losses. Out of the 10 trials, this comes up 4 out of the 10 times. Ooh, let me fix that. There are 4 favorable outcomes, that's better, based on this simulation. So therefore, that probability would simply be 4 out of the 10. For probability, it's always favorable out of your total outcomes. So that's why my 4 is what I'm wanting, and then 10 comes from the 10 trials that I have. So does this probability that the team will win 2 games change when exactly is replaced or at least? So we have to go back to our terminology. Exactly means right on the nose. This means that no matter what, it has to be exactly 2. So I'm even just going to put equal to wins. Whereas at least is greater than or equal to 2. So this does change it. So yes, this will change it because there are more games that have 2 or more wins. Not only do we have the 4 games, but I have another one. This is 3 wins. 3 wins would fall into the category. 4 wins would go into the category. So this changes the probability. Rather than 4/7, this will change it to, or not 4/7, rather than 4/10, it changes it to 4/7. because of the fact that this at least means greater than or equal to 2. So it does change that probability. Wording is important, and I will even make that additional note. Wording is important. All right, which brings us to example number 2. Now, example number 2, there is no triad involved, so we're just going to look at it together. This one is stating that, okay, the Hornets and the Tigers will play a 5-game series, with the winner of the 3 games named the state volleyball champion. The 2 teams are evenly matched. Use a simulation to find the probability that the Hornets will win the 5-game series. So we have to understand what's going on. They first start off with the probability model, which is fantastic. We either have the Hornets win or the Tigers win. If they are evenly matched, then that is going to be a 50-50 shot of either of them winning. With this simulation for step number 2, they just did a coin flip. Keep in mind, 50-50, it is perfectly okay. 1/2 probability, you can totally use a coin flip. Because a coin flip also has a 50-50 chance of winning. So they just flip a coin. They said if it lands on heads, then the Hornets win. If it lands on tails, the Tigers win. Okay, that makes sense. Heads for Hornets, tails for Tigers. They flip this coin. Since it is 5 games, they flip it 5 times. In the first trial, we have 3 heads and 2 tails, meaning that the Hornets win. They do this 7 times because more trials equals better data. I had to make sure I was saying that right. Better data with the smiley face. So they went ahead and do it 7. Ooh, I moved the entire thing. They go ahead and do this 7 times, which is great. The more trials that you do, the better your data is going to be. So finding that probability based on the 7 trials, the Hornets win 4 out of 7 times. Now, this could change. This is not a set probability. We are not guaranteed that the Hornets will win the series. This is just an educated guess. Without actually performing the experiment, we do not know for sure. Which this does bring us over to example number 3, and it's try it. So this one looks like a doozy. This says an energy bar company is printing an equal quantity of 6 different collectible cards. The company will randomly package 1 card inside the wrapper of each energy bar. What is the probability that all 6 collected cards will be packaged in a box of 10 energy bars? Well, we have 6 cards. Let's write down the important information. So there's 6 cards with 10 trials. We want, what is the probability that we get all cards? What is the prob of getting all 6 in the 10? Oh, all 6 cards. Let me be specific. All 6 cards in the 10 trials. So keep in mind, they do not specify how many times they want us to try this. They just went ahead and tried 8 different times. And with here, they just used a random number generator. Now, I've done that before in class. I've used a random number generator in order to pick random students if I just did not want to set up the wheel. So we know what this random number generator is. So doing this 1 through 6, they press this random number generator 10 times and get this set of data. If we notice here, full set of cards only comes out a single time. That is a 1 out of 8. That is really not a great probability. You only have a 12.5% if looking at this data set. Say if you did 20 times and it only came up twice. Well, that is a 1 out of 10%, and that's not really good either. So with this, you just got to really practice, and you really got to see what the scenarios are and then go from there. So looking at the try it, we got in a tennis tournament, 25% of Sarah's serves were aces. Now, all that ace means is that she got a point that very first serve. Design a simulation to predict how many aces you can expect Sarah to serve out of 50 serves. So this 25% is important. This means 1 out of every 4 serves is, okay, I know what's going on. I keep on accidentally hitting that power button, is an ace. So, I mean, we can set up a spinner, to be completely honest. We can have one spinner. There we go. And then it can be separated into 4 sections. And these 4 sections, one of them can be an ace, and you simply spin it 50 times. So we can use a spinner, use a 4-section spinner, and spin it 50 times. Now that is a lot, to be completely honest, but it would give you your accurate data to be able to say, okay, well, maybe you spin it and it lands on an empty spot. You know that's not an ace. You spin it again, it lands on another empty spot. Say that third time around, you spin it and it hit that ace. You would just record that down in your observation and go from there. Now, this is what all the sections are going to be. We're going to go ahead and hop right into the questions. We're doing great on time. You're going to do the do you understand, but we're going to look at the do you know how. This states that Carl hits the target 50% of the time he throws a ball at it. So maybe he's a baseball player. Carl uses a coin to simulate his next 3 pitches. He assigns H for hit, that's important, and T for miss. The results of 12 trials are shown below. So keep in mind, these are 12 trials. And each trial has 3 tries, it looks like. So, for example, this first trial, it looks like he hits it twice and misses once. The one below it, it looks actually the same exact thing. It's 2 hits, 1 miss. Whereas, let's look at another one. Let's just look at this one here. This one looks like it's 1 hit and 2 misses. So that's what each of those things mean. So based on the results, what is the probability that Carl will hit the target with exactly 2 of his next 3 throws? So there's that word exactly. We are looking at exactly 2 hits. So that means looking at our coin, we're looking for that H. So 2 H's, 2 H's, 2 H's. Down below, that is not 2 H's, so I would not highlight that. I would highlight each that has 2 H's. Well, count them up. I've highlighted 1, 2, 3, 4, 5 out of the 12. So therefore, this probability would be 5 out of 12. All right, looking at number 5, it says, on average, Margot scores a goal for her field hockey team 2 out of 3 shots. That's pretty good. So 2 out of 3 shots made. Margot uses a number cube to simulate her next 3 shots. She's assigned 1 to 4 as goals and 5 and 6 as missed shots. Why does this assignment of numbers on the number cube make it a valid simulation? So, okay. So if you're looking at this, she makes 2 out of 3. We've already got that. Therefore, that probability of her goal will be 2 over 3, which means 1 out of 3 shots will be missed. Now, the way you're probably going to see it on the test, this will be probability of made shots, where this is probability of missed. So just keep that in mind, that if you see that big P with the parentheses of what the favored is, that's just the probability of whatever it wants. And for this one, we got made or missed. So with the number cube, all that is a dice. We are going to have 1, 2, 3, and 4. Where if it lands on a 5 and 6, that means she has missed the shot. So this is accurate simply because 1 through 4, well, that is 4 out of 6 made. Well, 4 out of 6, what is that reduced to? Well, that's reduced to 2 out of 3. Same ordeal with the 5 and the 6. This is, well, it's 2 out of 6 because there's 6 total numbers on a dice. This would be your missed. What does 2 over 6 reduce down to? Well, that reduces down to 1/3. So even though it's worded a little wonky, uses a number cube. Once again, I wish they just used that as dice, because a number cube you can have, well, I guess a cube will have 6 sides no matter what, but it still would be a little bit easier if you just called it a dice. But that's how you would analyze it. She analyzed 1 to 4 as goals, meaning that this is shots made. Whereas that last 2, 5 and 6 would just be shots missed. And keep in mind with a dice too, dice is evenly weighed, or at least we say it's evenly weighed, to where each number has a 1 in 6 probability. Each number has a 1 in 6 probability. So it would be even. It would be nice, even dice. All right, which brings us to our very last page. Now, this goes all the way to 13, so I will just do the odd one since the last one's going to be an odd one as well. Okay, good. I'm zooming in on the entire thing. I am going to lock this real quick just so it does not move around on me, and we're going to go from there. So looking at number 7. Number 7 says, survey results state that 80% of people enjoy going to the beach. The random numbers below represents 10 trials of a simulation of asking 2 people if they enjoy going to the beach using the numbers 0 through 9 for their responses. So with this, 80% of people like going to the beach. So let's just draw out these numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Even though it's labeled 0 to 9, there is 10 possible numbers. That one's kind of confusing. I wish they just did 1 through 10, but that is A-okay. I understand why they did it 0 through 9, but you really have to count. So this is 10 different possibilities. We are told that 80% like the beach. So 80%, another way to look at that, well, that is going to be 8 out of 10 people like going to the beach. So let's just pick the first 8 numbers. 1, 2, 3, 4, 5, 6, 7, and 8. Meaning the last 2 numbers are people that do not like the beach. That 8 and 9 will represent people that do not like the beach. Which that actually helps us answer the first little part here. Let the numbers from 0 to 7, what we highlighted in green, represent people that like the beach. Whereas let the numbers 8 and 9 represent people who do not like going to the beach. So based on the simulation results, the probability that exactly 1 of 2 people enjoy going to the beach is what? So there's that key word again. Exactly 1 of the 2 people. So let's just kind of look at the data set. At this current moment, and I'll even use the highlighters, 0 through 7 are people that like it. So every time I see a 0 or 7, I'm going to highlight that number in green. So 8 and 6. 6 is a number I like. 5 and 4, both of them are good. 2 and 2, both those I like. 0 and 9, I like that 0, but do not like the 9. 4 and 0 are good. 5 and 3 are good. 0 and 7, 6 and 5, 5 and 6, 1 and 5. So we got a lot of people that like the beach, whereas we only have 1, 9, and 1, 8 there. Keep in mind, numbers 8 and 9 do not like the beach. 0 through 7 do like the beach. The probability we're looking for is exactly 1 of 2 people. So we're looking for a green and a red. This 8 represents someone who does not like it, but the 6 represents someone that does like it. That is 1. 0 represents someone who does like the beach, where 9 represents someone who does not. That is 2. Those are my only 2. So that would be 2 out of the 10 people, which is just 20%. All right, going on with our odds, looking at number 9, we have an inspection of items at a company shows that an item has a 50% chance of being defective. That's not good. A spinner with equal size sections numbered 0 to 9 can be used to simulate the event that the next 2 items inspected are defective. Now, good for them, to be honest. I don't really know. That's not good. If you ever have a product that is 50% chance of being defected, that is not great. But let's go ahead and set this up. We have sections 0 to 9. We can kind of use the information we got above. That is going to be 10 sections. Oh, even sections. Uh-oh. Let me redo that, because that's 8 even sections. So, Star Miss Edwards, 1, 2, 3. I literally just did the exact same thing. We're gonna pretend this is 10 even sections, guys. Okay, so each of these is gotta be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It is a 0 through 9 selection. How would you assign the numbers to represent the defective and the non-defective items? To be completely honest, I would give every other one. I would do even. I like even numbers, so let's do that one as the non-defective. Whereas the odd numbers are the defective ones. Now, you could do things different. You could if you wanted 0 through 4 to be your good to go, and then your 5 through 9 be your not good to go, that would be fine too. I'm just a little quirky, and I want my odd numbers to be defective. We don't like those. And then my even numbers to be good to go. But I mean, really, it's that one's kind of an opinion based. As long as you have that spinner and 50% of your choices is defective and the other one is non-defective, you're completely fine. Based on the simulated results below, what is the probability that the next two items are defective? So this is very much on your own. It depends on what you labeled your spinner is. For instance, probability that the next two items are defective. Well, that means both. Both are defective. Depending on what you did, 2, 3, 1, 2, 3. So this one, both of them would be good to go. 9 and 2. 9 and 2, so 9 would not be great, but 2 isn't even. 8 and 7, 7 and 0, 4 and 9, 4 and 4, 4 and 3, 5 and 5. So far I got 1, which I mean isn't that bad to be completely fair. This would, for me, would be 1 out of 10. If you did it differently, you're going to get a different answer though. So just keep that in mind. And I figured that out because I'm looking for basically 2 odd numbers. 8 and 8 are both even. 9 and 2 is just 1 odd number. 8 and 7 is 1 odd. 7, 0 is 1 odd. 4, 9 is 1 odd. 4, 4 is both even. So they're both good to go. 4, 3 is 1 odd, but 5, 5 is both odds. Because keep in mind, odd is defective. So this answer will vary. I would love for you to try on your own, but if you want to just use my work, then you will have other things as well to try out on your own. So just keep that in mind. That was 9. Let's look at 11. How is the difference between the simulated probability and the theoretical probability of an actual event related to the number of simulated trials connected? So the more more data equals, or more trials equals better data. And I mean, that's true for both. We even said that for theoretical probability, the more trials that you have, the closer to the actual probability you're going to get. This is the same exact thing. The more trials in the simulation, the closer you're going to get to the theoretical probability. So the more simulated trials you perform, the closer to the theoretical probability. And I'm even going to say you should. I keep on hitting that center button. You should get, and I'm even going to underline that should, simply because it's an educated guess. We're going to have educated guesses. It's your best educated guess. And that's just kind of how probability is. I mean, unless you have an actual event, you have the facts right in front of you. That's all it is. Best educated guess. That's why I hated probabilities, because I need facts. All right. Which this does bring us over to the last one. It says about 50% of people surveyed in a certain county work for a small business. A random number generator was used to simulate the results of the next 4 people surveyed. This is important. The numbers 0 to 4 represent people who work for the small business, and 5 through 9 represent people who do not work for a small business. And then we have our trials. What was that? It looks like here we have 1, 2, 3, 4, 5 times 4, 20. trial. So we just got to keep that in mind. Based on the simulated results looking at part A, shown above, what is the probability that at least one of the next 4 people surveyed works for a small business? So that term, at least one, that means I'm looking for greater than or equal to 1. One person working small business. Now, this is not more than 1 in our data sets here. You got to understand that this created our parameters. We are looking for a 0 to 4 at least 1 time. So I'm going to take that green highlighter, and anytime I see numbers 0 through 4 in an individual batch, I'm going to highlight it. So 6, 4, 1, 1, that's a couple of them. Got a 0, 0, 5, 8, 2, got a highlight, got me a 0, 3, got a 3, 5, 2, 2, 2, 0, 3, 7, 5. I have a 4, got me a 2, 1. Notice what I'm doing. This is my criteria I'm looking for. Anytime I see a 0 to 4, so that means 0, 1, 2, 3, and 4, I'm highlighting it. 7, 5, 9, 6. Notice here that this does not have any of these numbers. That means these people surveyed, none of them worked for a small business. 2, 1, 1, 2, 3. Holy cow, we have 19 out of 20 people, that's our probability, who work for a small business. If we were to turn this into a percentage, this is 95% of the people surveyed. That is, wow, it's a lot of people working for small business. How would you design, or how would the design of simulation change if the percent of people who work for a small business was only 7%? So maybe you change the number of people that work. I mean, you kind of do. Rather than saying 1/2 of 0 through 9, you're going to have 70%. So maybe having numbers 0 through 6, because let's rewrite those numbers. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At this current moment, 0 through 4 represented small business. That is half. That is 5 out of the 10. No, there shouldn't be a 10 down there. Quick fix. There we go. Now there's 5 out of the 10. So rather than 50%, they're now saying, well, what about if there was 70% of these people working for small business? We're going to have to broaden our span. We can represent this as 7 out of 10. So 7 out of 10 people, we can say now work in a small business. So 1, 2, 3, 4, 5, 6, 7. All we have to do is add 5 and 6 into that mix. Make 0 to 6 represent people who work in small. And you're doing that because if we need a 7 to 10 probability, that means we have to include 7 out of 10 of my options, which is what that does. All right, but that is all of 7-7. Y'all go ahead and work through the problems that I did not do. Keep in mind, and I'm even going to just look at something smaller. Let's just look at number 9 again. All this represented, I'm going to pull an individual trial. 8 represents 2 devices. This was as if you're putting a comma. Since it landed on an 8, it was an even number. This is non-defective. Same ordeal with the other one. That just means that this one is also non-defective. So this is 2 different devices. Say if we're looking at number 8, when you do number 8, an individual trial, this will represent 3 different things. So looking at number 8, it's talking about voters. So 3 will represent 1 person. 8 represents another person, and then that 0 will represent a third person in a single trial. So 3 people, but 1 trial. So just keep that in mind. That's what it's asking for. Sorry, I just took a second to explain that. I just thought about, well, man, oh, hi. I have a little pup here, and she just wanted to come say hi. So sorry I took a second to explain that in case you missed it from above, but hopefully that will clear up some things for you. If you have any questions, shoot me a message. Otherwise, good luck, guys.